Right, so this lecture is on the Aldol reaction, but before we can begin on the Aldol reaction, we need to talk about a little bit about the special reactivity of the alpha carbon. So, what's the deal here? If we look at just a general structure, so here I'm looking at a carbon that is adjacent to a carbonyl. Okay, so this is the alpha carbon, the one that is right next to the carbonyl. And we find out that since it is one away from the carbonyl carbon, that there is actually some special reactivity that happens here. So the big question is, why is this special? Why is there any special reactivity? Well, it turns out that there is something special about this in the fact that it is relatively, and I speak relative as far as what you're considering around it, relatively acidic. And so if I draw this alpha carbon here, it turns out that I can treat this with a little bit of base. And I can actually deprotonate by having a base, take off a hydrogen, and put a negative charge on the carbon that is adjacent to the carbonyl. So the big question is, why is it that there is some acidity to that? Why is it that I can have a negative charge on this carbon? Because normally you don't see a carbon that has a negative charge on it. Well, it turns out that we can draw a resonance structure by kicking in these electrons and moving them up to the oxygen there. And so now I have this sort of special species here that I can actually look at and say, aha, there is some special reactivity there, and I've got some sort of relatively unique acidity that I can sort of look at here. So this is the big difference now, in that this is not a regular carbon-hydrogen bond. And so this leads us to basically a new term. And what I've formed when I do this is what we call an enolate. So I have basically a carbon-carbon double bond with an oxygen that has a minus charge. And now we're going to call that an enolate. So one of the things that you need to worry about in this case is that the acidity of this actually depends on what is really around this alpha carbon. So it depends on the type of carbonyl, and we'll get into that a little bit later. But more importantly, we're looking at what type of carbonyl it is, but for now, we're just going to focus on the fact that alpha carbons adjacent to these guys that are adjacent to carbonyl have some actual acidity, and it's because you can draw a resonance structure, and as is shown there, you can form the enolate. So, for example, if I draw, basically here's a structure of acetone, I have two alpha carbons that are adjacent to the carbonyl. And so these alpha hydrogens of acetone indeed have some acidity, but again, we're speaking in relative terms here, so they have a pK of about 20.
This is getting a little complicated, Rocco.
Now, what you need to do is watch out for asymmetric carbonyls. There are a couple of pitfalls here that you kind of want to look out for. And one of them being that, let's say I make something that's asymmetric. So I have two alpha carbons. I have one that has a methyl group and one that doesn't. So now I've got something that, if I treat this with base, I have two potential areas that I can form the enolate with. So here is one, which is the more highly substituted double bond. And then I have another on the other side. And so these are basically going to be constitutional isomers of each other. So I've got to worry about, what kind of enolate I'm going to form. So that's something to kind of keep in the back of your head for now.
I'm not listening to you. You're crazy.
So now we're going to look into enols and enolates. So I've been talking about this enolate thing. Well, what is the deal here? Well, it turns out that enolates are anions. Up to now, you've been seeing me talk about deprotonating the alpha carbon and forming this negatively charged species that we call an enolate. So I'll give you basically an example momentarily, but you can see up there that an enolate has this negative charge on the oxygen. Enols, basically, in a sense, are alcohols. So you can see the structure here where we have an OH that I've circled. And we basically have two ways that we can form these guys. So enolates, we typically form these with bases. So if I'm in a basic solution, you can imagine that I'm not going to have an OH that's present. So I'm going to use something that's kind of strong, and that's going to actually take away the proton that's here. So I'm just going to put B minus for now. And I'm going to have this B minus go ahead and take away the proton that's attached to the alpha carbon, and then actually going to show the resonance structure that would ensue. And what you see is that you actually have what's an enolate. So I don't have a hydrogen that's attached to that. I have a negative charge on the oxygen that's there. And so you can see that this is actually going to be an enolate. So I have a negative charge plus the base that has the proton there. So here's my enolate. Okay, so now let's look at enols. So enols actually can be formed from acidic solutions. So you can do the sort of the same thing. You can go back and do this with an acid solution. So here I'm going to take a carbonyl that has alpha hydrogens. So you can see the carbon there that's adjacent to that carbonyl has alpha hydrogens, and I'm going to treat it with some acid. Notice that I'm going to protonate the carbonyl oxygen first because that's my Lewis base, right? I've got these lone pairs on there, so those lone pairs are going to pick up the proton from the acid. Always remember to think about this in terms of Lewis base, Lewis acid. So once I draw the actual product, what I see is that now I have this protonated carbonyl. And if you remember from direct addition and using a weak nucleophile, remember that this is an activated carbonyl now. And so now water is going to come in actually. And water can come in and take away this proton. If it does so, it's going to enolize rapidly. And so what I see is that in fact, I now have the actual enol. It has a proton on it. Okay. About some terminology here. So I've already talked to you about enol, enolate. So let's look a little bit more. The species that has the carbonyl. When we're referring to these things, we're going to refer to this as, if it's in the carbonyl form, it is the keto form. And however, if it is a species that is enol or enolate or whatever, in particular, mostly for this, it's going to be the enol form as far as what we're referring to. The one that has the OH here, we're going to refer to this as being the enol form. So, what do you need to know about this? Well, we have keto, enol sort of forms, both of those. It turns out that most of the time, like 99% of the time, most aldehydes and ketones, they exist predominantly in the keto form. So I'm going to give you an example of this. And so the example that I'm going to show you is, for instance, if I were to take acetone. Right, so everyone knows what acetone is. You ladies, you can remove your nail polish with it, right? So it turns out that if I were to mix acetone and water, what do I have? Do I have acetone or do I have the enol of acetone? Well, it turns out that I have 99.9997% acetone. So basically, I just have acetone. Right, and so the enol form is 0.00003. So I don't have any of that.
No, and then. And then. No, and then. And then. No, and then. And then. No.
And so basically, the difference between the two is that they are tautomers. 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 And so that's the difference between the two. They're not sort of isomers or anything else. They're tautomers. Now, if we go from one tautomer to the other tautomer, then we call this sort of transformation something that we refer to as tautomerism. So we go from one to the other, that is a tautomerism. Now, I just told you that most of the things, they would like to be in the keto form. However, some tautomers, you have to watch out for this now, some tautomers are more stable in the enol form. And I'll give you an example here. So, if I look at something like this, where we have a diketone. Now, imagine that I've got a little bit of acid in there or just in solution. Look at the proton that I have here. I've got hydrogen bonding. So one of those guys is going to want to stay over there. And it's the hydrogen bonding that makes it more likely. So this is more likely on one of them that it's going to want to stay in this favored state. Right? And that's because of that favorable hydrogen bonding. Here's another example. Look at this ring that I'm drawing. Right? So I'm going to put this, here's the keto form. Right? And if we look at our equilibrium arrows, we can see that actually the phenol is preferred. Why would that be? Well, if you have the phenol, of course, you've got more aromaticity there, right? So something that's aromatic is going to definitely be more favored. It's more stable. So you have to look at that. All right. This brings us now to another concept. And this is the beta dicarbonyl compounds, some of which you just saw on the previous slide. Yep, these guys. Those are the ones I'm talking about. So if you look at these guys, what you'll notice is that we have multiple alpha carbons, right? So the question that you might be asking, if not, I'll ask it for you, is which of these is the most acidic, right? So I have alpha carbons on the left, on the right, and I have alpha carbons in the middle. So which is the most acidic and why? So let's draw this guy out. So now I'm going to draw all of the alpha hydrogens.
Oh! What did we eat?
Okay, so if I treat this with a little bit of base, which one is the base going to take? Well, let's do an example first. Let's say it takes this guy on the end. So here I'm going to draw. Here's my keto now to my enol form, which I'm going to form the enolate in this case. So I've got a minus charge there. And then so if it were to go on the other side too, it'd be the same thing, right? So same as the other side as well. So either one is the same difference. So all of those three are basically the same. Okay, so I can see that I have one resonant structure that I can draw for that. All right, now let's look at the guy here in the middle. So here's the hydrogens. I'm going to treat this with a base. All right, so what's going to happen? Well, I'm going to deprotonate first, and here's the thing that I want you to notice. I'm going to put this negative charge, I'm going to put that guy right there, dead set in the middle. There's my negative charge. Okay. So what you should see now is that I actually have two different places to go as far as resonance structures. So I can go up this way to the one on the left. There we go. We've got one on the left there. Let's draw that enolate. Beautiful. There's our enolate there. And then this can kick back down, and I can reform the other enolate, basically, which is on the other side. But first, I've got to go through the sort of intermediate one where I go back to the middle. And there's that guy right there in the middle. Now, I can go on the other side. So I've got two possibilities now. So there you go. Now I've got two different resonant structures. And so what I can see from this is that since I have this beta dicarbonyl, that the middle has more resonant structures. Because the middle has more resonant structures, what this means is that it's actually more acidic because the conjugate base, therefore, is more stable. And those hydrogens, therefore, are more likely to be deprotonated. Hey, thanks for watching.